the dust which sits in the stratosphere can block sunlight, and it can do that for 1 or 2 years before the dust settles down. You expect this dust to reflect some of the sunlight and therefore cool the Earth. And you know there are measurements which tell you how that changes the radiative forcing. You can plug that into global circulation models and see by how much the temperature should have decreased. And in fact, when you look at the global circulation models, you see that when you had large volcanic eruptions, the model give you that the temperature should have decreased by quite a lot. In fact, the models give you that such large volcanoes should decrease the temperature between 0.3 and 0.5 degrees. In reality, whenever we had large volcanic eruptions, the average temperature decrease, this is the temperature before and after the 6 strongest volcanic eruptions since Krakatoa, you see that the temperature decrease has been, on average, 0.1 degree. Why is that? That's so because the global circulation models are too sensitive. They're more sensitive than reality. Okay. Now, if we're talking about sensitivity, let's try to understand where the source of the problem resides. We know that when we heat the Earth, because, for example, we double the amount of CO2, we change the energy budget. If Earth didn't change anything except increase the amount of CO2, what we would expect is to see a temperature increase of 1.2 degrees Celsius. Now, in reality, Earth changes as well. If you heat the planet, then you also heat the oceans. You get more evaporation. Water vapor is a good greenhouse gas, so you get a positive feedback which increases the temperature even more. But if we have more water vapor in the atmosphere, we also form more clouds. And it turns out that clouds are the dominant uncertainty in global circulation models. One model can give you, has one recipe for the clouds, and it will tell you that the clouds will change by a little bit. Another model will tell you that the clouds will change by a lot. And this gives a change in sensitivity. I mean, you can play with this recipe for cloud cover and get sensitivities between, say, 1.5 or 1 degree increase to 5 degree increase for doubling the amount of CO2 just by playing this with this recipe. And this you can see with this graph. This is a paper, this is a result which was published already in 1989. What you see here, this is the sensitivity of the climate models, and this is a range of climate models that were in existence back then. And here what you have is the inherent sensitivity or feedback that the model has through cloud cover. Because you see that all the models sit on very close to a straight line, it tells you that this thing, this parameter, this sensitivity or this feedback through cloud cover is the dominant source of uncertainty in climate models. Okay, so the reason the IPCC cannot predict the temperature increase is that because nobody knows what is the correct recipe to use in order to describe by how much the cloud cover is going to change if you heat the planet by a given amount or you change the amount of water vapor. Another problem is that there's no fingerprint which proves that CO2 is the thing which does the warming. Now, someone would say, just a second, we saw Al Gore's science fiction movie, and in that movie, we have seen Al Gore show us this graph where you have a CO2 reconstruction and temperature reconstruction from ice cores, which were drilled in Antarctica in this case. And he tells us with his authoritative voice, the relation is complicated, but we see that when there is more CO2 in the atmosphere, the temperature is higher. Why? Because he wants us to believe that CO2 causes a large temperature increase. What he doesn't tell us is that when we have ice cores with a good enough resolution, which is usually ice cores coming from Greenland and not from Antarctica, you see that always you have a lag such that CO2 lags behind the temperature and not vice versa. Okay, so how can the CO2 affect the temperature before it itself is affected? I mean, we know that CO2 must have some effect on the climate, but this correlation that Al Gore has shown us doesn't prove anything or doesn't quantify anything in this direction. Now, the reason we see this effect is the same thing you have in this thing. You have a Coke bottle, and if I forget this Coke bottle in a car in a hot summer day, probably most people here don't know it because there are not a lot of hot summer days here. But if I forget it in Israel and I open the Coke bottle, what will happen is that everything will fly out. And the reason is that what we have here is CO2 which is in the air and CO2 which is dissolved in the Coke, and we have much more CO2 which is dissolved in the Coke. And this CO2 is in some balance between CO2 which is dissolved and CO2 in the air. Now this equilibrium depends on the temperature. Now in the oceans it's more complicated because there are a lot of chemical reactions and it's not just simple dissolution in the ocean, but still in Earth we have that there is 70 times more CO2 in the ocean than there is in the atmosphere, and the equilibrium between CO2 in the atmosphere and CO2 in the ocean is temperature dependent.